is a programming language which was started around 1965, so it's been around a long time, and it's used a lot for theoretical physics. And when I went back to university some time ago, I discovered it there and love it. But it's very like APL in many ways. You can type straight into the session, and you have to end everything with a semicolon. Order of execution is not like APL, right to left. It's priority, power gets priority, times gets priority, that sort of thing. So you can assign a variable. A is, I don't know, 1.
Can I ask the font question, Graham? Can you criticize the font?
No. Okay. Sorry, it's a pain, isn't it? Anyway, I just at this point trying to show you it's similar to APL. You can create a matrix, call it core, and we'll say it's got 2 rows and 3 columns. So now it's expecting that to be a matrix. If we assign it, we start off by saying, let's say it's 1, 2, 3 on the first row and 4, 5, 6 on the second row. So it's a matrix, and it's got a rank. No, it hasn't. Okay, forget that. Oh no, rank. R-A-N-K. And you can multiply it by itself if you transpose it. So core times transpose core will give you that, and you can take the determinant of that, for example, and will give you that, which, you know, that's fine. If you do the factorial of 200, you get a jolly big number. So it deals with big numbers. But not just that. ABC gets x plus y plus z, or let's say plus 3z. It doesn't have a value error. There's no such thing as a value error. ABC is now that. And ABC, this is to the power 6. There it is. We can differentiate it. ABC cubed with respect to x is that. So it's a very powerful language, and you can create multidimensional arrays and do all sorts of things. You can't do the same sort of size that you can do with APL, but you can do very powerful algebra. Okay. Now, in string theory differs from ordinary physics because in ordinary physics you've got particles on world lines, and the interval, the absolute invariant interval on the world line is measured ds squared equals dx mu dx mu. Just take my wife there. That is how you start physics for particles. With strings, they're pieces of string, and they have a world sheet, not a world line. So now we've got 2 variables. We've got tau and sigma here, and we have to now talk in terms not of that, but well, I can't be bothered writing it down, but I'll write down the bottom line, and that is that up here we've got F equals ma. Remember that? Force equals mass times acceleration. That's the equation of motion of a point particle under force F. In string theory it becomes more complicated, and we have F mu, because we're obviously relativistic here, equals d by d psi a, because this psi is a vector, two-element vector, sigma and tau basically, whereas before it was just dx by dt, one variable. And the momentum looks something like some sort of generalized mass times the square root of the induced metric, which is GAV, times dx mu by dx xi b. That is what this turns into. I should point out that this is actually md2x by dt squared. So there is close analogy all the way, but how string theory progresses is you know how to progress classical mechanics to a quantum theory, so you can try to do the same here. But there are anomalies, so it turns out that you have to have 26 dimensions. So you have an anomaly-free theory. But that theory is for bosons only, so you want to introduce fermions, so you introduce supersymmetry, and this becomes embedded in superspace. What's superspace? You might like this. Complex numbers have real numbers and imaginary numbers. Right? Superspace has real complex dimensions, but it's also got Grassmann dimensions. What's so good about Grassmann numbers? Well, it's a Grassmann number times another Grassmann number is equal to minus the second one times the first. So the anti-commute. I'm glad to think about that for a minute. That has the consequence that theta squared equals 0, which you think, oh, that's useless, isn't it? And most people thought that for 100 years, but then what you needed in physics is to be able to rotate bosons into fermions. If you put them in superspace with Grassmann dimensions, you can do that. Okay, take my word for it. So this can be supersymmetrized and goes into supergravity in 11 dimensions. This can be supersymmetrized and goes into string theory in 10 dimensions. So the bosonic theory is intrinsic. Okay, lots of dimensions. That's your introduction to string theory. Now get back to this. In 1986, Polakov produced a paper which added to normal string theory a rigidity to the string. So the string actually had rigidity, and this theory, he felt, had instantons in it. And my supervisor suggested I look for these instantons. Well, I didn't know what he was talking about, really, but I read a few papers and decided that the best way to see what these instantons are solitons. They are states in the equations of motion which don't decay into nothing immediately. Like a circle, string circle, there's a tension in the string, so it pulls it all together, nothing stopping it, it just disappears. So it has to rotate or something to keep it apart. The normal bosonic string theory, if you break the string, the ends have to go at the speed of light. Now, just at this point, it might be worth just saying that a galaxy, the whole universe is supposed to be string theory, right? A galaxy has this spiral structure. Now, imagine that's a string that's been rotated. That's the possible sorts of things that physics might realize in the future if string theory ever makes contact with reality. Anyway, the string, by the way, is about 10 to the minus 32 centimeters long if it's going to describe elementary particles. So I was given this problem, and I thought, what if you had a string and you wanted to do a stable thing, you'd have a knot in it. So I went to see the knot theorists at Durham, and Jerry Kirton said, well, the simplest knot is a Taurus knot. If you take a torus and you wind some string around it and join the ends, then you've got a Taurus knot, and the simplest one of them is a trefoil knot. So I love this which I've learned how to do. draw one of them, and one of them, and one of them, it starts turning into a knot. Right? Now, what is a knot in this sense? Well, if you have an equation u to the p plus b to the q equals 0, well, p and q are relatively prime, and u is a function on one complex plane, and b is a function on another complex plane, then if you think of these two planes as sort of intersecting, the two dimensions C2, this is C2, two complex planes, right angles, then if you draw a small ball around the origin of this four-dimensional thing, then you'll find that this curve crosses the sphere in a knot corresponding to PQ. So that's a very simple thing to start with, because what I'm looking for is an embedding of the complex plane in R4. Okay, so if let me just start this again to get rid of all that. If I set P to 2 and Q to 3, whoops, P is 2, Q is 3, and I read now run this program. Let me show you what the program is before I run it, otherwise it wouldn't make too much sense. Here's the program. It's pretty short. In reduce, create an operator x, at least declare x to be an operator, declare s to be an operator, say that x depends on s1 and s2, set z to be s1 plus I s2, z to the q equals z to the power q, z to the p equals minus z to the power p. That solves these equations. So we've now got a solution to these equations in terms of z. And we stick them into x1, x2, x3, x4 as the coefficient. Stick them in somehow, and then reduce this dx by dxi, and then we take the square root of g, which we need there. We get this matrix. We eventually find the integral, and we'll look at the integral at the end, and we just run the program. We click enter. Goes in, continue, yes, continue, yes. Run the program. We end up with this function. You integrate that, and in fact, turns out to be a beautifully, it's an integer solution, and it's exactly what you want for a soliton. So I found all these, an infinite hierarchy of a Taurus knot solve the registry equations and actually give lots of interesting answers. So there's some of the results. You can see they get pretty hairy. If you're going to do that by hand, you'd have difficulty and so on. So reduce is a really important tool here, and it does calculations you could consider doing. So that's, are we halfway yet? Around halfway. So I didn't stop there because I was interested to understand particle physics, and although these knots may actually give interesting models for particle physics, and I notice, not that I'm saying this is directly necessarily anything to do with me, but Bohr atom of glue balls, this is a very recent paper I just picked up, and they're talking about Taurus knots, but in a special way, it's sort of different starting point, and they're talking about certain states in the spectrum of the F meson, for example, being glue ball, knotted glue balls. Anyway, so there's some sort of reality there. Right, let's move on, because here we're talking about the embedding of C, of the complex plane in we'll talk about an embedding, an interesting, non-trivial embedding of the complex plane in R4. What about, in exactly the same way, the embedding of the Quaternions in the Octonians? Because here we're going from 2 dimensions to 4, here we're going from 4 to 8, is so analogous that you can do exactly the same trick. You can say, now let's call the Quaternions car, to make sure we understand. We're talking about something different here. This is a Quaternion, right? Car to the p plus rho to the q equals 0. We can easily find the solution to that in terms of Quaternion. Anyway, let's say it's exactly the same. So, can we do the same trick? Well, it gets far more complicated. Here we start. Let's look at what I call a self-dual HO brane. This is standard terminology in our brain. While I was doing this knot stuff, physics was moving into what they called super P branes, and this was very exciting stuff because the whole of physics was supposed to be explained not in terms of strings necessarily, nor in terms of membranes, nor in terms of lumps, nor in terms of the 4-dimensional extended object, but in terms of p-dimensionally extended objects in superspace. And then people had brain scans, serious brain scans, which told you which were quantum consistent theories, and you only had a few of these, and one of them was Quaternions and Octonians. So it seemed to be a good choice. So here we have a Quaternion to the power 3 and put into the first 4 elements of x, and then a Quaternion to the power 2 minus Quaternion to the power 2 into the next 8. There should be a 3 up there. Sorry. Up there. And then it goes in, then it creates a matrix, and then it goes into this cap B. Let's look at B, see what that does, if we make any sense of it. This is a reduced program. Here we have an 8 by 8 by 8 by 8 array of numbers, which is interesting. And here we have an 8 by 4 by 4 by 4 array. We've got, and down here we're trying to find the square root of G, RG, that's the one that takes most time, doing the square root of this matrix, which is filled with algebraic expressions. To find the square root of that matrix is asking quite a lot. Anyway, we'll go through all this stuff. We'll go through. So we'll take this one, we'll run it. It shouldn't take long. It's now creating a thing for Octonians to multiply them, and it comes back eventually with the answer, and it tells us that, in a sense, it didn't work. Here's Txxx, this expression. Here's R root G, this expression. They're very similar, and when you analyze it, it comes down to just one sign. And this one sign is the problem for all these infinite hierarchy of Quaternionic functions embedded in the Octonians. And so, you know, there's no analytic theory of Quaternions, so mathematicians can't say, let's write nice, beautiful proofs because they don't have the theory. It's like before you had the theory of complex numbers, you couldn't do very much proving with integrals, and there's still problems with integrals. So, whatever my conclusion here was that I was so close to finding a solution which was self-dual in these high dimensions in an area where nobody else had got any sort of, well, nobody was looking at that. I'd been successful before with the knots, these quaternionic knots, which I called quads, even before I found any, which I never have, actually. However, I found complex things that solve all the equations of motion and all the self-dual equations. I found boring quaternionic solutions, which have solved all the equations, but I haven't found these quads, which I believe are there. I'll just show you. Well, this was my first paper on the subject, but the only paper on the subject of knots, and this was in Physics Letters B, and it was quite successful, and I had requests for my paper from all over the world. And then this quaternionic bit, what I did was, at the end, I concluded that first I couldn't publish the paper that said I didn't find it, even though it's very, very close. That's not the sort of paper people publish. So I just published a less interesting solution, and with it this new theory of everything. Now, let me just... Oh, I don't know whether... Have I got time? Another 5 minutes? 2 minutes. 2 minutes? Okay, I better get to the point. And that is... 2 minutes. The point is that APL and reuse should get together. And I wrote a paper for a vector some time ago where I suggested how this might happen. There's a free software called GNAC, which stands for GNAC is not a CAS. That's what GNAC stands for. GNAC is not a CAS. CAS is a computer algebra system. So it's saying we are not a computer algebra system, but actually they are the foundations of it. So you can get the foundations for this sort of thing. And I think APL should go that way. And the last, well, I feel strongly anyway that functions are very important, and physics is based on functions, not numbers. You want functions which describe the world, not numbers, and so there's a huge area there for development, and functions may become more and more important with people having vast volumes of data, because you can't store petabyte after petabyte. You need some way of reducing it, and maybe having a function that fitted it is just about as good. And so functional stuff must become more and more important. And I've got a curve which I can show you, and I'm willing to give £100 to anybody who can tell me the equation of this curve. I can tell you very precisely how to describe the curve, but I can't find what the equation is. And as a sort of, to make you interested, £100. Done. You want to know what the curve is? Yeah. Can I show you then? Just to show you how very stupid I am, I've reinvented the wheel. And here's my new wheel, the curve that I'm interested in, very specific. You put the thing together like this, and there you have a new wheel. you'd think that's, you know, a funny looking wheel, but it rolls quite nicely on the slope, and if I had the curve exact, I believe it would roll very, very smoothly. So if you can tell me what that curve is, I'll give you 100 quid.
Did you do it now quickly or? Do we have any questions for Ryan quickly?
Algorithms doing a matrix inverse of Quaternions and Octonians?
Oh no, I wouldn't say that. No, not built in.
I don't know.
But that's not difficult. The inverse of Quaternion is not difficult. It's just like a complex number. The inverse is
Well, you just use a factor method.
yeah, you want to keep top and bottom by the complex number.
I was concerned about the associativity and unity. So I guess it's good algebra. So it's not.
I mean, at that level, I think you have to write your own stuff, you know, to do that multiplication.
Go factor. You just go factor. Or replace each element or multiply it by a factor.
To multiply.
Well, one way of doing matrix inverse in terms of
Yes. Yes.
well, that's not limited.
Oh yeah, sorry, matrix.
Matrix inverse or
It's got lots of functions.
Quaternions or
We're working on it.
Not Quaternion. So any
you know that AGLC has Quaternions, not Taurus?
So I heard today. It's interesting.
Yeah.
But what it won't have is the derivative with respect to Quaternion.
Possibly not. How do you find the label?
I've forgotten. Labels. I haven't used it really because for students, I think I'm mathematically sure so that they say it's great for graduates, you can draft here, but for the freedom of having a multi-dimensional array and, you know, types products and things like that, reduced.
I find labels
Okay, we're going to have to stop there, I'm afraid. Thank you very much, Graham.